Hello, and welcome to my talk, A Tour of Functional Design. Thank you for coming here. I am so excited to be here at Scala-Italy. This is my first Scala-Italy, and like Gabriel said, it's my first time in Italy. So I'm really happy to be here. Thank you all for putting... Had a great time last night at the speaker dinner, and then I hung out with some of the local, I mean Italy, because apparently everyone comes from all over Italy to these things. So I hung out with the local Scala community a couple days back and just had a wonderful time. I really appreciate this. So today, I'm going to be talking about a tour of functional design. The most common question I get, actually, is people look at the open source work that I do, they look at the talks that I give, and then they come up to me and they're like, John, why haven't you moved to Haskell? That's it. Why haven't you moved to Haskell, John? Why are you still in Scala? Well, I'm going to give you a secret. I believe in Scala. And let me clarify that just a bit. I actually believe that Scala is an extraordinarily powerful language for doing pure functional programming. In other words, it's not just Haskell that can do pure FP and solve business problems. It's also Scala. And in fact, I believe that functional Scala holds tremendous promise for the future of the Scala programming language. Not only is Scala 2.x a great solution for doing pure FP, but in Scala 3, we get a whole new bag of goodies that are going to make it easier than ever to write maintainable, large-scale, compositional software using the power of functional programming in Scala. And that brings me to this talk, and basically every other talk that I give where I'm evangelizing the functional side of Scala, saying that yes, you can solve real-world problems using the Scala programming language, using pure FP in Scala. And I know what you're probably thinking. You're probably thinking like, how could you ever live without var, right? And all the other stuff in Scala. And my answer to that is, well, why would we ever want to live with var when we have things like transactional memory, for example, that can be updated atomically across 100,000 fibers, or when we have atomic references and other bags of goodies that we get in functional Scala that let us solve the business problems we have, but do it in a way that's easier to understand, easier to reason about, easier to test, easier to compose, and easier to make correct the first time, and also keep correct over time. So that's why Scala, that's why functional Scala, and that's why I'm extremely happy to be here today and talk about how we use design techniques in the functional subset of the Scala programming language. Agenda. So today I'm going to be talking a bit about structure. What is structure, and how do we use it when we're going about functional design? Then I'll take a look at structure in the context of a common problem that maybe some of you here solve at your day job. Somewhat realistic, I just sort of pulled this at random from a bunch of suggestions. And we're going to look at the structure in this problem when you solve it using a procedural approach. So procedural would be what you would do in C or Pascal or Fortran or all these other not necessarily functional programming languages. Then we're going to take a look at that same problem, but we're going to switch things up. We're going to shift it over into the realm of pure functional programming. And we'll see what changes about the design of this solution when we do that. And then finally, the most important part of this talk is going to be that final section where we look at the functional one and we say, well, you know, there's some good stuff about this, but are we truly leveraging 100% of the power that functional programming gives us? Or is there some way we can do better? And then I'll talk a little bit about how we can shift our design more from functional imperative to functional declarative and learn something about the process of design as we go. And then finally, I'll wrap up with a summary. Now, this is a tour, by the way. This is not a workshop. So the most I hope to leave you with at the end of this is inspiration. I hope that you look at business problems in your day job and you think, maybe behind all this code here lies some more elegant structure, something simpler, something that we can describe using types and functions and immutable data structures And maybe, just maybe, if we're willing to take the time to learn that, we can get some very tangible benefits out of that process. And if you are convinced that there's at least more to Scala than you maybe have seen before, then I'll consider this talk a success. So what is functional design? Well, functional design is basically the art of finding the best structure that allows us to describe an entire space of solutions in such a fashion that it is composable, orthogonal, and minimal. That's functional design in a nutshell. So functional design is that search for structure. It's a search for structure that has certain properties that give us the ability to compose in an orthogonal and minimalist fashion. And we'll take a look at some examples of that later, so don't get too hung up on this now. But for now, I want to dive a bit into what is structure. Like I say, we're trying to find structure, good structure in FP when we're doing functional design. But what is structure? Well, structure basically just describes everything we know to be true about a data type. The set of everything we know to be true about something. That's what its structure is. And if you like to think in terms of the Scala programming language, then I want you to consider the any type. The any type is a type without any structure. Why? It sits at the top of the inheritance hierarchy. It has no structure. And then as you extend any with different types, everything extends any, either directly or indirectly, you start adding structure. And the more you extend it, the more structure you add. And of course, way down there at the bottom of the inheritance hierarchy in Scala is this other type. It's the dual of any. It's nothing. And nothing is basically the type with all possible structure. And yes, it's a contradiction, and it's useful in a type system, but it's the type with all possible structure. Any is the type with no structure. Now, not all structure is created equal. There's differing levels of utility to structure. There can be some structure that's useful and other structure that's not useful. And in my opinion, the best type of structure is extraordinarily rich. It's very, very powerful. But it can be described very simply and very concisely. And the reason for that is, if we can describe a whole universe of possibilities very simply and compactly, then we can reason about that compact description. We can think about it, we can test it, but yet we can use it to solve a huge number of problems. And that's why, in my opinion, the best structure is that structure which is very, very rich, but simultaneously very, very compact. There's structure everywhere. So, literally everywhere. Including in this very room. So obviously there's a lot of statements that we could make about this room. We could make statements about everyone in here, not just everyone in here, but the position of every atom. Not just the position of all the atoms and the molecules and so forth, but the positions of the chairs and even the laws that define atom-to-atom interaction. We could do that. And that would be a lot of structure. Too much, actually. To describe all that, we don't even know all that, but to describe all that would take who knows how much, and therefore we wouldn't have a very good ability to reason about that. But let's scale down the problem of talking about the structure of this room. We're going to zoom in and focus on one particular aspect and see what we come up with and see if we can learn something about the structure along the way. In particular, let's consider all the people in this room, their current state. So everyone is either standing up, I guess that would be me, or sitting down, and then we've got a bunch of people in different rows and columns of the auditorium. So we have some state, we have what could be described as a data type, if you will, and now we can start talking about structure on this data type, that is, statements that are true of it. And one way to do that is to introduce an operation called sit down. This is the sit down operator. And we apply it to one of you, and that gives us back one of you that's sitting down. And if we have a sit down operator, then one of the things that we could say is true about that operator is that if you sit down and you sit down again, you are in a state of sitting down. In other words, if you apply this operator twice, you get back the same thing as if you apply it once. This is idempotent. This is the sit-down operator is idempotent. And the corresponding inverse of that, if you will, not actually inverse, would be sit up. Okay, one of you could sit up, and if you sit up 2 times, well, that's equivalent to sitting up or standing up a single time. And interestingly, we can get this little relation out of this, which is if you stand up and then you sit down and then you stand up again, that's the same thing as if you stand up. And that's not a true inverse, by the way. That's very important there. You don't have to understand why, but that's not an inverse. That's something even weaker than an inverse. I'll talk about that later. And conversely, we have this property. If you sit down, and then you stand up, and then you sit down again, that's the same as sitting down a single time. So we have here 4 different properties. We have 4 statements that describe the behavior of these operators with respect to the people in this room. We have we're describing them by statements that are true. These statements in functional programming are called laws. And laws are extraordinarily powerful because they make statements that are true in all possible cases, especially polymorphic laws. Polymorphic laws say, for all these possibilities, the thing on the left-hand side of the equal sign is always equal to the thing on the right-hand side. And that gives you an ability to describe an enormous amount of behavior in a very compact way. That is the essence of good structure in functional design. Here we have down idempotence, up idempotence, something called left adjunction. Ignore that if you've not heard of it, but basically it's, sit down, sit up, sit down. That's the same thing as sitting down. And then we have right adjunction, which is the reverse of that, the dual of that. So here we have 4 properties that characterize the behavior of sitting and up and down. What else could we do? Well, we could think about another operator. How about this operator, swap? So swap in a row. Basically, 2 of you who are sitting next to each other could exchange places. And that would carry with it the statement that the exchange of P1 and P2 is basically equal to P2 and P1. So it's the same arrangement. The only thing that's changed is the people have swapped positions. What about if a seat is empty? Well, we could introduce a sentinel value here, a 0, if you will, if you've heard of monoids and semigroups, such that you swap this and you move the position of the empty around without actually, you change the position of the person and you move the empty around. What if you swap things twice? Well, if you swap 2 people sitting next to each other twice, you should get back where you started from. And then we could do the same thing column-wise. So not just across the rows, but we could do that column-wise. And we could go through the same thing with the empty seat, the sentinel value there. And then what can we do with this? So we've identified a good amount of structure here. We have 4 different operators, and these 4 different operators are described by laws, very compact algebraic things that can compactly describe a whole universe of possibilities. What could we do with these 4 operators? Well, it turns out that these 4 operators are all you need to take one state of this auditorium and transform it to any other state that you could possibly imagine. So no matter what state we can come up with, some people sitting up, some down, some over there, some over there, we can use these 4 different operators to achieve that state. I'm not saying it's going to be fun for all of you. There's going to be a lot of swapping involved, but it's possible. And what does that tell us about these 4 operators? It tells us that they are composable, first off. They're composable because what we can do is we can take this thing, the state of a person or a pair of people, and we can apply an operator to it and get back something that we can again use with the same operator. In other words, the stuff that we get out of these operators, we can feed back into the operators. That's what composability is in a nutshell. And composability is important, by the way, for the following reason. When you have a composable system, it means you can have a small number of operators that you can reason about, you can test, you can think about, you can understand that. But because it's composable, you can solve a huge, infinite, potentially infinite landscape of possible problems. This is the solution to software complexity. This is why functional programming is so amazing. It's composability. It's because using small number of cases that you can reason about and test, you can solve infinite number of problems. And it's a key aspect of a good functional design, composability. This is also orthogonal. No operator here does the function of any other operator. So this would be called single responsibility principle in OOP. It's the same thing here. No operator does the function of any other operator. You cannot use any operator, in fact, to get you the functionality of another operator. They're all totally independent. And it's minimal in some sense. I mean, you can experiment with a different basis here by smashing more onto one operator, but I would consider this a minimal basis. This is what we need to solve this type of problem. All right, with that definition of structure, let's go into a more real-world problem. Because I know after seeing the example of all the people in the auditorium, you're thinking, well, that's nice in theory, but my business code doesn't look anything like that. Like, I'm not going to be using these techniques in my business code. And maybe that's true, but maybe it's not. I think that as I've spent more and more time doing functional programming, I've discovered that sometimes the structure is there if we know how to look for it. And if we've read the right books, the right tutorials, if we've seen the right talks, if we have help from our coworkers, sometimes we can discover structure in our problems that allow us to build very good functional designs when it didn't even appear on the face of it that it would be possible. And so what I've chosen here is the following class of problems. So imagine you're working for a company and one of your jobs is to collect data from a bunch of different places and integrate it. So maybe you're doing this for purposes of model building, or maybe it's just something you display on your website or mobile app. But a good part of your job is writing code to implement high-level flow diagrams like this. In this case, there's some URL, you need to go grab some data on there, you need to parse it as JSON, and you need to convert that to your domain model, and then you need to grab some stuff from the database, you need to mash those two things up together, and finally you need to update the data in the database. So this is an example of something that's in the business world. This is very concrete. In fact, so concrete, we're going to take a look at some Scala code to do this. So here it is. And actually, most of the code would not fit on a slide, so I cheated. You'll see that in a second. But basically, this is what you have. First off, you have this big block up here at the top, which is downloading a file from a URL. Only in this particular case, we happen to know that this website is notoriously flaky. So we have to try a few times. In fact, we have to try a lot of times sometimes. So we do a basic retry loop here. And we keep on trying to pull that until we get it down, at least in the event that we get an I/O exception. If we get some other type of exception, we just let it crash. So that little hunk of code is going to end up, if it succeeds, it's going to pull back that file downloaded from that URL, which will be step one in our data integration project. And imagine that this is more representative of the class of problems that we're trying to solve. So we have this guy, yeah, but we also have 100 other methods like this. They're all somewhat similar. They differ in details, but they're all pretty much more the same. What we're grabbing from and how we're mashing it up with existing data, all that stuff varies, but basically the structure is the same. So then we take and we convert the output of that web request, that HTTP client request, into JSON. We map over everything and we basically ignore all the errors potentially that we got out of that. We try to convert them into some sort of domain model, a sale record, a record of a sale. And after we do that, there we go, okay. After we do that, then we're going to iterate through each one of these sale records. We have some new data that we got from that website. We cleaned it up. And we're going to update every products record in our own product catalog. And we're going to incorporate the net price, which we downloaded off this third-party website. Does that make sense? And then, of course, here's where I'm cheating. Because there's hundreds of lines of really awful JDBC code that I'm hiding in there. But just know it exists, and know it's just more of the same. So what are the problems with this bit of code? Well, there's some duplication here, and the duplication is going to be basically across across our set of 100 or so different data integration methods, we're going to have a lot of duplication for dealing with logic that has to retry. So anytime that we're going to run into a flaky connection or a flaky database connection, maybe the database is down, we're going to have to write some sort of logic like this. And it's hard to factor out this type of logic in the world of procedural programming because we're always doing side effects. Our effects aren't values, so we can't write effect combinators that allow us to do things like retry. But this is what I've seen more often than not in strictly procedural code bases. It's just lots of copy paste to deal. And our retry strategies, by the way, might differ by URL or other things, so it's not going to be 100% duplication. Also, we have this interesting thing here that is not really considered, it's not considered a problem in a lot of communities, and that is we have some implementation details leaking in here. Basically, this can fail, this process can fail, getting the content of a URL, and that failure is evident here in our code. We're doing a low-level thing. By calling this client, this HTTP client's download file, we're doing a very low-level thing. And that low-level thing might fail. And so we deal with that here. But this is actually not the ideal place to deal with that failure. I mean, this is the obvious place to deal with it, and this is where most of us do deal with it. This is not the best place to deal with that failure. Why? Because we are mixing levels of abstraction. There's a bit of business logic here that you can see. If you pull out all the sort of icky implementation details, there's some business logic here that you can see. And ideally, in best case scenario, you would look at this function and you would only see the business logic. You would not see tangling of different layers in your application. You would see straight up business logic. And yes, somewhere we would be dealing with the retry. This is why one of the reasons aspect-oriented programming and other things were invented was to try to untangle that. Now, they didn't work out so well for other reasons, but nonetheless, this is a real problem that's not widely appreciated. We also are going to have duplication, like I mentioned, across similar solutions. We're going to have some obvious testability problems, which we can solve, obviously. We know how to solve this. You use Mockito or one of the other numerous mocking libraries out there, JMock and so forth. The Scala mock, all the Scala stuff out there. But nonetheless, it's not easy to test code like this. And if this were 100 lines of code instead of this, it'd be even more complex. And then finally, we've got another type of leaking where right now when we iterate over these sales, we have to make a choice about parallelism. Are we going to do this sequentially like I'm doing here, or are we going to do it in parallel? So basically, code that should be dealing with business logic concerns is going to have to make a choice that depends on lots of things unknown to this bit of code. It doesn't know how many cores are on here. It doesn't know the properties of the database. It doesn't know any of that stuff, but it's going to have to make a choice. And any time code that doesn't know enough to make a choice is making a choice, then that's a design smell. So all these are the high-level problems I see with this code. And a lot of them stem from the fact that it's procedural. Some of them stem from even more deeper problems than that. Basically, you have those caused by procedural problems, those caused by imperative problems. So look at this code. What is the structure of this code? It has structure, right? Everything has structure. This code has structure too. But the interesting thing about this code is that it's not easy to describe that structure. In fact, this is probably how I would describe that structure. That's the structure of that code. I mean, maybe there's more that you can say about it, but I'm looking at that code and I don't see more than that. I just see, it's like, if the only way to specify something is to refer to its implementation, that's not an actual specification. And it's the same type of an idea here. All right, so let's bring out the tool of functional programming to this problem and see what happens. But first, before I do that, I want to say something that is not said enough, in my opinion. And that is that functional programming and imperative programming are totally orthogonal. They don't clash in any way. They are totally different axes. So on one axis, you have functional programming up here and procedural programming down here. That's a legitimate axis. Functional programming and procedural programming are diametrically at opposite ends of the spectrum. Functional programming is all about programming with values and functions, and procedural programming is all about programming with side effects. Now the other axis, though, that functional programming is orthogonal to, that axis is, on the one hand, imperative programming, and on the other hand, declarative programming. Those are the two main axes that characterize code. Functional programming, you can have functional code that is very imperative. And you can also have procedural code that's very imperative. And functional programming, because it is not at odds or in any way clashing with imperative programming, can actually be used to make your imperative programming better. And that's what functional effect systems are all about. So if you've heard of things like Zio or Monix or Cat's.io, functional effect systems allow you to take the ordinary imperative programming that you do every day and make it better, safer, more modular, more type safe, more expressive, more powerful ability to abstract over patterns that you wouldn't be able to do if you were operating in the world of side effects. So with that in mind, what we're going to do is, knowing that functional programming can be used to make imperative programming better, it's not at odds with imperative programming, we're going to take FP and apply it to the very imperative, the preceding solution that we looked at. It was both imperative and it was procedural, because it was doing a bunch of side effects and it was doing them all sort of one at a time in sequence. So it's very imperative, do this, do that, do that. And it's also side effecting. We're going to take and we're going to migrate that over into the world of pure FP without changing the fact that it's imperative. It's going to end up looking something like this. First, we declare our function, which is in this case going to be polymorphic in F. We're going to require an effect constraint on it. And we're going to write a little retry helper function here that's going to be able to do the exact same thing as the other logic. The difference is, though, that this can be reused because it's operating on values. So I put this function here locally, but I wouldn't have to. I could pull that out and never write it again. It would work across all effects, not just the one download file thing. And then notice at the main body in this function is for expression. It's actually building a value. In functional effect systems, we don't do stuff, we describe stuff. We build values that describe operations. And so here I'm building a value that is going to describe the process of integrating this daily sales data into our database. And I do that by using the retry combinator on the result of calling a different download file. This is my own download file that returns a functional effect. It's not actually performing a side effect. And then this bit of logic, it doesn't change, and then instead of using a for each loop on that sales, I use traverse, which is the effectful version, the purely effectful version of for each, and I basically do the same thing. So what's the structure of this? Well, there's certainly more structure here. You may have to look harder to see it, but we have things, and these things are being composed together. And those things are these Fs, these functional effects. It's like having futures and composing them together to get other futures here. You compose them in a certain number of ways. And so there is structure here. The structure, however, is very low level. It is not really connected to this business domain problem. It's way, way, way down here at the level of functional effect systems. And that gives us a lot of things. But ultimately, this is an imperative solution to this problem. And should you do this? Absolutely. You should absolutely choose to put lipstick on that pig because it's safer. It's way more expressive. It's more powerful. It's less duplication. And when you're able to turn a side effect into a thing that's a value, it opens up a world of possibilities for doing incredibly complex stuff in a way that's sane and type safe and allows you to get rid of all the duplication. So you absolutely should do this in your day-to-day coding. And if this is the best that you can do, or the best that you want to do, or the best that your team is willing to do, then awesome. You're already in the top 0.01% of code bases in terms of maintainability and type safety and so forth. So do that. But on the other hand, if you look at that and you're like, well, you know, could we do better? Is there a way to do better? Is there a way to take some of the structure that's in this business problem and surface it up in the data types and the operators that we use to express the business logic? Then that's the next thing we're going to take a look at. All right. So that was the functional imperative solution. In order to pull the imperative out of that, so we end up with just the functional, we need to be considering a more declarative solution, something that's less about sequencing and more about building a static description of the solution. And to do that, we're going to go all the way back to that diagram I showed you at the very beginning. So this is the problem. And this looks a lot cleaner. This looks a lot cleaner than all the code that we ended up with to implement this. It would sure be nice if we could take this high-level description of the problem and translate it almost one for one. Obviously, in code, you have to specify details, and those details require space, and you have to form expressions together and do stuff in order to make sense that's adding additional layers of specification that are not implied here. But it would be nice if the structure of our code were able to more easily reflect the high-level structure of this diagram. Well, look at those things connecting them. We have an awful lot of arrows here, an awful lot of them connecting this. We have a sort of flow of information. We have actually a graph where arrows connect different nodes in the graph, and information travels along the edges of that graph. That is the basic problem. That is the essential structure here. And if we view it that way, we can imagine each arrow as some sort of data type that maybe accepts an A as input and produces a B as output. And then in the general case, this is a many-to-many relation. So every arrow will feed it a bunch of A's, maybe 0 or more A's, and out of the other side, we're going to get 0 or more B's. So this thing, let's give it a name. It doesn't matter what we call it. I'll call it a pipeline, because it's kind of like a pipeline that transforms A's to B's. And then we need to start thinking about what can we do with pipelines? Well, one of the most basic things we can do is if we have two pipelines, we can compose them together into another pipeline. So if we have a pipeline from A to B and another one from B to C, we should be able to compose them together. There should exist a composition operator that allows us to get another pipeline from A all the way to C. And that should have the same effect as feeding all our values into the first one and then feeding all the outputs of that one into the second one. Also, if you looked at that problem in detail, then one of the things you're going to notice right away is that there's an awful lot of transformation going on. That is to say, when we get back the raw data from the client, we have to interpret that to JSON. And then once we have JSON, we have to translate that into our sale data type. And then there's even more stuff behind the scenes that I didn't show all the messy details of, but that means that we're going to need some type of arrow that allows us to transform from one type to another. And we also want it to satisfy a certain important law. This is structure that we want this transform arrow to have. We want it to be the case that if we transform an A into a B, and then transform the B into an A, and then transform the A into a B again, basically end up where we started with. And this should look a little familiar to you. You've already seen this. This is people standing up and down. This is a different way to see that. It's the exact same law here, just expressed differently. And not just transform, but we're going to need an identity arrow, and the identity arrow is basically going to be some arrow such that when you compose it with any other arrow, you get back the same thing. So whether you compose on the left or the right, then you get back the same thing. That identity arrow, by the way, and the ability to compose these things make this a category in category theory. We're also going to need a way to send some data to the database, since all these hundreds or so of scripts, they update the database a lot. And we're also going to need a way to pull out some data from the database. And we should have the following high-level law, which is that if we grab something from the database and then we put it to the database, that should be the same as not changing it at all, basically. And then finally, we need another another operator here that's capable of taking two pipelines and joining them together into a single one. That will allow us to build graphs. That first structure that we saw was a graph, and there was a point where two pipelines were being joined together. We need that capability to solve the problem, so we need an operator like join. And it's less easy to characterize in diagrams what this thing should satisfy, but it is possible. All right, well, this is all well and good, but what about code? Can we actually take this design and translate it into code? Let's try. We'll start off with a pipeline here, a data type called pipeline, that can be viewed as a transformation from some number of A's to some number of B's. It is not specified here any other details than that. All other details are irrelevant. The only thing we care about is this is a pipeline that takes A's and produces B's. That's it. We don't want more details. Details will just get in our way and cause us to have too much structure that's hard to reason about and hard to figure laws out for. Then we're going to have this operator here. It's called, this is backwards composed. It's called and then in Scala. But I like the arrow operator here just so I can form pipelines like this. This syntax is available in CATS and scala-z for things like this. Then actually we won't strictly need, because you can derive this one, but I added it here, a map operator that allows you to take the output of a pipeline and turn that B into some sort of C, and then you're going to get back a pipeline from A to C. And then this join operator here. To implement this, what we do is we create a bunch of different case classes. Every case class merely represents the given operator. So we have one for identity, one for reading from a URL, one for reading from a database, one for transforming, one for composing, one for dumping to a database, and one for joining. So we're just describing here. We're not actually doing anything. We're building a static graph structure. This thing here is a tree. It's a directed acyclic graph. And it's going to allow us to build all sorts of things, including the one we saw at the very beginning. And nowhere here is specified any implementation details. This is purely declarative description of space of solutions. We already saw what some of the laws would be for these different things. And then just to use this in a more simple fashion, we could introduce some helper functions to just construct these different terms in this enumeration directly. And notice here in the transform one, it takes something called a codec. And there are lots of different ways to encode a codec. This definition of a codec is weak. It's weak in the sense that when going from A to B or from B to A, there's a possibility of failure. You might not be able to turn a bunch of bytes into a JSON object. You might not be able to. Or if you have a JSON object, you might not be able to turn it into a sale record. There's a possibility of failure here encoded with either. And it's symmetrical, which makes it weaker than some other codecs, which allows a nice property that you can take any codec A to B and you can flip it to get a codec B to A. And then you need a few different codecs in order to solve this problem. I've just sketched out their types there. They were implicit in the previous solution, but just so you can see here, we're dealing with real values. All of these things can be tested independently. All right, well, let's take a look at the solution. Ta-da. All right, so here we have it. This is a value now. The first one, it was just a side-effecting method in procedural land. And here it's just a value that returns a pipeline. This is a pipeline from unit. It's a closed pipeline. It doesn't require anything but unit, doesn't produce anything information. It's a pipeline that's ready to be run. You don't need to do anything with it. We have this little helper function that can update a product given a new sale price. So I just factored that out because I want the following code to be really clean, but it's just a little helper function that updates a product with a given sale number derived from the URL. And then I've divided the problem into subproblems, which is, I don't need to do that, but functional programming makes it very easy. You can always pull out an expression and stick it into a val in functional programming without changing the meaning of your program. That's guaranteed to be true of all functional programs and not true of non-functional programs. So I did that here so I could have three different subproblems. And the first one, I create a pipeline that pulls from the URL, transforms the bytes to JSON, and transforms the JSON to the sale. And I just stitch those together using that compose operator. And then here I have a pipeline for records in the database that pulls data out of the database, transforms it from the result set to the product type. And I take advantage of that flip on my codec because my codec goes from product to result set, and I flip that to go from result set to product. And then finally, I take the sale and I join that together with the records by the ID, the product IDs, which was previously happening inside that helper function that I didn't show you the body of, that was hundreds of lines of JDBC code. Here, it's short enough I can start to show you more details of what's going on behind the scenes. I do that join, and then after that, I update the product, I transform it, update it with my helper function above, I transform that product to a result set, and then I feed those result sets into the product's database. So there we have it. Basically, I've stitched together all these different things. Excuse me. And built a pipeline from sub-pipelines, a small number of base pipelines. I've used my operators, which follow algebraic laws, in order to construct together a big pipeline that solves my problems. And these operators, the 6 or whatever operators I show you, can solve not just this problem, they can solve an infinite class of problems. I'm not saying they can solve all problems that you'll run into, obviously, but they can solve a pretty big, wide range of problems in 6 operators that you can reason about algebraically. And what we get out of this is nothing more than a data structure. And this data structure, unlike the things that you get out of functional effect systems, has no continuations embedded in it. Functional effect systems allow you to do great things because they're monadic, they're very powerful. They embed the power of continuations inside them. But unfortunately, that leads to some nasty problems around testability. It has no continuations embedded in it. This is a static graph. And you can introspect every bit of this tree to discover the entire structure. And that allows you to do some really interesting things, including, for example, pulling the retry logic out and putting it somewhere else. This part of the code knows that that URL has some trouble. And so you can basically, when you run this pipeline, you can insert some special case logic to deal with problematic URLs, and then different URLs could get different retry strategies. None of that clutters the business logic. There's no cluttering of the business logic here. And what you get out of this is basically, in every way in which the procedural one had problems, some of those were fixed up by the functional one, but this one cleans up the remainder. This can be tested trivially. It doesn't do anything, just builds a data structure. This is pure business logic. It doesn't tangle concerns. It doesn't mix layers of abstraction. And also, essentially what we've done is we've built a mini programming language that is hyper-optimized for solving this class of problems. And a new person on the team can just join and be like, well, yeah, this is how you do it. You know, there's only one way to do it, so we're going to do it this way. That's very, very powerful, and it can help maintain the code over time. And the reasonability and testability you get out of this is also very, very key in maintaining this type of code. And yeah, ultimately, at the end of the day, you have to take this description and compile it. So in this case, I compile it down to a ZO stream, because the streaming is the most natural way to implement this. But you don't need the power of streams in our business logic. We don't want them. We just want something high level, something smaller, safer, and more reasonable that has stronger guarantees with laws. And then once we have the stream, we can go ahead and do whatever we want with it. So this has structure. This has a lot of structure. And that structure is well characterized by algebraic laws. This design here, thanks to these operators and these base cases, is an example of pretty good. I'm not saying, and you can do better, spend time on this, you can do better, but pretty good functional design because it demonstrates the fact that we have a structure here that is powerful but also concise. So we can reason about it and test it, but use it to solve a huge class of problems. And also the operators here, they're all composable. They allow us to explore giant spaces of problems using a small number of operators. It's orthogonal, so different operators don't do different things. I mean, they do different things. They don't overlap in their functionality. And finally, it's in some sense minimal. I think you could make it a little bit more minimal if you worked on it. But I think it's fairly minimal as it is for this class of problem. All right, so what have we learned? Well, I hope we've seen that structure is everywhere. It's in this room with people sitting down in the auditorium, and it's also in your business logic, even though it's not always obvious. And functional design is about finding good structure. It's about finding good structure that is very descriptive, so it's so teeming with possibilities, but also very, very compact. Both of those are important. The fact that it has enormous predictive power is important because it allows us to solve a wide class of problems that we run into. But also the fact that it can be described small, in a very small space, means that we can get our minds around it, and we can write good tests for it, and we can know when it's correct. And that combination of sort of big up here but tiny down here, think of it as a ratio of sort of predictive power over how many bits required to describe that, is a measure of the goodness of a structure. And in functional design, we look for that good structure that allows us to solve problems in a way that is composable, that is, using a small number of operators, we can snap together all our different solutions to different problems. Orthogonal, so different operators shouldn't do different things, and minimal in the sense that we don't need more operators, we've got everything it takes to solve everything in this space. You saw how imperative programming, there's structure there, but it's rather hard to characterize. And imperative programming has a whole host of problems that arise from the fact that you're not dealing with values. And merely shifting to a functional effect system, we gain a lot of power and we introduce some structure. We introduce some structure and we gain some power. But even in the pure FP, we're still operating at a pretty low level. Basically, at that point, we're doing functional imperative programming, which is enormously powerful, and I encourage everyone to do functional imperative instead of imperative. Functional imperative is way better in every possible way. But we're still doing imperative programming. In imperative programming, you all probably know the reasons why that's not great. It makes testing harder. It makes reasoning about software harder because you have to think of state changes and all the sort of drawbacks that come from imperative programming. We don't have to stay at functional imperative. If we're obsessed with using monads to solve our problems, then we will stay there. But if we're willing to sort of relax the constraint, maybe say, hey, maybe we don't need a monad here to describe a set of solutions to this problem, then we can go more into functional declarative. And functional declarative, that's where we're basically building our own little language. Whether it's a language of people sitting up and down and swapping and doing this and that, or whether it's a language of pipelines and us composing pipelines together to get other pipelines and combining pipelines to get pipelines according to well-defined laws, that's power. And you can bring that power back with you, I hope, to your day job, maybe not just after this little tour, but I hope here you've seen that there is structure in the world around us. And in some cases, we can find that structure and we can talk about it in a very principled way. And then we can use it to build very, very powerful solutions in the pure functional subset of Scala. I hope you have enjoyed my presentation. And I don't think we have time to take questions, but I will take questions in the hall. Thank you all for coming.